Hey guys, hope everybody has had a really restful and wonderful break so far. Starting the new year with some calculus. So this is going to go over the first day of our new topic, and we will build on this when we get back to school. So if you still have some questions, don't sweat that. But this will at least give you a good introduction. So we're going to start off with something back from Unit 2, which was the idea of implicit differentiation. And I want you guys to try this problem on your own, and then we will jump into this, go over it, and build on that. So pause the video, try it, and then hit play when you feel like you're done. Okay, so looking at this, I'm using implicit differentiation to take the derivative with respect to x. So what I'm trying to do here is I'm trying to take dx, right? Take the derivative with respect to x of whatever expression I've been given, right? And so in order to do that, we are going to need to use implicit because we've got two different variables going on here. So let's start with the x times y. That is a product, right? And so to take the derivative of that, I'm going to use the product rule. So here I've got the first, which is x, and the second, which is y. And product rule tells me to take the derivative of the first times the second plus the derivative of the second times the first. So the derivative of the first is going to be dx with respect to x, which we know is just 1, right? So derivative of the first times the second, leave that alone, plus the derivative of the second, the derivative of y with respect to x, times the first. So here I've got, again, 1 times y plus, I don't know what dy dx is because I don't know what y equals, right? We're making an assumption here that y depends on x, and so we wind up leaving this as dy dx times x. And that was the big idea from implicit differentiation, right? That we're taking the derivative of something that is dependent on something else. So same thing with this plus y squared. So I know the derivative of the outside part there is 2y, but what I need to remember is that the inside of that is the y, right? It's y squared. And so I need to multiply by the derivative of the inside. So I wind up with plus 2y dy dx. And then the derivative of the right side, which is the derivative of 1 with respect to x, and that is a constant, so that is just 0. And then from there, this would just be algebra. So we would factor out the common factor of dy dx among the two terms that have it while moving the term that doesn't to the other side, and then divide both sides by what's left in my parentheses. And this would give me an expression in terms of x and y for dy dx, right? So this is where we left with implicit differentiation, the idea being that we're taking the derivative with respect to x, but that we have a y in our actual equation. And so the big idea with this was noticing that we needed to use the chain rule, right, multiplying by the derivative of the inside, because we are taking a derivative with respect to a variable other than the variable in the expression. And that's something that we're going to look at in application in what we do next. So let's look at this prompt. It gives us a bunch of information about a square. So a square's area is varying over a period of time. A is equal to s squared. Implicit differentiation would give us that dA dt equals 2s ds dt. So let's try to break down what this is saying a little bit. So I have a square, right? And the idea is that its area is varying with respect to time. Now it's staying a square. So what I know is that this is changing areas, right? So it's going to get bigger, or it could get smaller, or it could do both, but it's going to stay a square. And as time goes on, that will impact it. So what I know, again, is that this is varying over a period of time. So let's look at what these different things represent. What does S represent? So in this original formula, A equals S squared. S is the length of a side. Notice S does not represent the side, right? It's the length of the side. What does A represent? It's the area of the square, right? And then we get into these differential quantities. And so it's like, what's the question with these? Or what do these mean? So what does ds dt represent? What does dA dt represent? So notice that we said that the size was changing and we are taking the derivative with respect to time. So I'm looking at how these quantities change over time. ds dt here is going to be the rate. It's a derivative, right? So it's a rate. Rate the side length changes with respect to time. So as time goes on, what's the rate at which the side length is changing, right? Remember that this is a slope, so it's change over time. And what does dA dt represent? It's the rate, the area of the square is changing with respect to time. So what we're looking at here is the fact that because we know that side length and area are related, we also know that the rate the side length changes and the rate the area changes will be related. And we use implicit differentiation to find that. So area is side length squared. If we take the derivative with respect to time, then dA dt would be 2s times ds dt, because that would literally be the derivative of it, right? So these types of problems where we're looking at how rates are related to each other based on how quantities are related to each other, we call related rate problems. And the idea with these is to look at what's changing and try to work with what we already know to determine how those rates will be related. So go ahead and read this strategy for solving related rate problems on your own. This is right off your notes, but we're going to hop in and look at some examples at how what we know about some situations can help us see how these rates are related. So first one, we have an oil spill, right? And it's spreading in a circular pattern. Radius is increasing at a constant rate of 5 feet per second. So it should make sense that if you spill something in one spot, it will go out in a circular pattern and your radius is going to change throughout that time. What I want to know is how fast the area is changing when the radius is a particular amount. So we can use a lot of the strategies we already use for word problems to start here. So this organizer is going to help us get going. We will eventually not use it, but at least get us started. So we're going to draw a picture, state what we're being asked for, and then define our all variables. And we are going to look at two different types. The first are ones that are general, things that are always true, and then things that are only true at a particular point in time. And for related rates, it's really important to distinguish those. So let's start with the picture. We know that we have a circular pattern to this oil spill. I have a radius, and that radius is increasing, right? It's going to get bigger over time, and we can go from there. So I want to know how fast the area of the spill is increasing. So if I'm going to write that symbolically, what I'm really saying is dA dt, the rate the area changes with respect to time. And I want to evaluate that when the radius is 25, so at a particular point. Now, in words, that means the rate the area is changing, the area of the circle, or of the spill, is changing when radius is 25 feet, right? So that's what I'm really looking for. So let's see what we know. So things that they've told us. They've told us that it's a circular pattern. Radius increases at a constant rate of 5 feet per second. So that's constant, that rate, and it's the rate that the radius changes. So it's dr dt, the change in radius over the change in time. And that is 5 feet per second, right? And then they tell me how fast, I want to know how fast the area changes when the radius is 25. Now that is not constantly true. The radius is constantly changing. That's only true at a point in time. So at a particular point in time, the radius is 25 feet. And it's going to be important to know that because that means that's not always true. I can't just plug that into an equation. So let's look at our variables here. We've got A, area. We've got R, radius. And then the derivative of R, right? Those are my big variables. So in order to relate these rates, I need to relate those variables. And so the easiest way to do this is to come up with a formula that has all those variables in it. So for a circle, I know that area is pi r squared. And then we're going to use implicit differentiation to take the derivative of that with respect to time, because we're looking at the change in time or over time. So on the left side, the derivative of area is going to be dA dt. On the right side, remember pi is just a constant, so the derivative of that is 2 pi r times dr dt. So you have to multiply by the derivative of the inside. And that formula relates my rates. So now we can just plug in everything we know. So we know dA dt, or we want to find that, 2 pi at a particular point in time. I know r is 25, and dr dt is constantly positive 5 because it's constantly an increase of 5 feet per second. So dA dt here is going to be 250 pi. And then think about your units. This is a change in area over time. So that's going to be feet squared per second. So what this is saying is that when the radius is 25 feet, the area is increasing at 255 pi feet squared per second. Okay, let's look at another one. This is very similar to that initial scenario that we looked at. So A is the area of a square whose sides have a length s. Assume that s varies with time. At a certain instant, the sides are 3 feet long and are increasing at a rate of 2 feet per minute. How fast is the area increasing at that moment? So very similar, right? We have a square, and I'm only going to label what I know. So A is the area, and the side lengths are s. And s is varying with respect to time, so the square is getting bigger and smaller. At a certain instant, the sides are 3 feet long. I'm not going to put that on my picture because that's not always true, right? It's only true at a particular instant. So at a particular point in time, s is 3 feet. And at that particular point in time, s is increasing at a rate of 2 feet per minute. So that would mean ds dt, it's increasing, so it's positive 2 feet per minute. Not always true, again, just at a point in time. How fast is the area increasing? So what is dA dt? Change in area over time at that moment, so at the time when s equals 3. So that's what I'm looking for here. So nothing that's generally true here, right? Everything was at a particular point in time. So let's try to relate these variables. I have s and ds dt. I want dA dt, which relates to A. And so the best formula to relate those will be our area formula again. Remember, area equals side squared because that has all of the variables in it. So take the derivative of that. dA dt is 2s ds dt. And now let's plug in. We want dA dt. And I have 2. At a particular point in time, we said s was 3. And ds dt was 2. So plugging in those, this is going to be 12. It's area, so the units there are feet squared, and time, our units are minutes. So at the time when the side length is 3 feet, the area of the square is increasing at 12 feet squared per minute. All right, let's look at another one. So let L be the length of a diagonal of a rectangle whose sides have length x and y. So let's draw a rectangle. L is the diagonal, x and y are the side lengths. We know that x increases at a constant rate of 1/2 foot per second. So constant, dx dt, is positive 1/2 because it's increasing. And we know y decreases at a constant rate of 1/4 feet per second. So dy dt, it's decreasing, so it's going to be negative 1/4 feet per second. So here, what we have is in this rectangle, one side is getting bigger constantly while the other is getting smaller constantly. So I want to know how fast the size of the diagonal is changing. So what's dL dt? At the instant when x is 3 and y is 4. And so I do know at a particular point in time that x is going to be 3 and y is going to be 4, right? So that's sort of the information that I'm given. I've got x, y, and then dx dt, dy dt, I want dL dt. So think about our variables here. I've got x, I've got y, and I want dL dt, which means I need to know something about L. So we need a formula that's going to relate all 3 variables here. And what I see when I look at this is knowing that this is a rectangle, that's a right triangle. So the easiest formula to use here is going to be Pythagorean Theorem, which is x squared plus y squared equals L squared. Now, because x and y vary, I can't plug in anything here. They're going to change. And so I am going to start by differentiating this. So 2x dx dt plus 2y dy dt equals 2L dl dt. And now let's see what we can fill in. So 2, I know at a particular point in time x is 3, and at that point in time dx dt is a half, plus 2y dy dt, right? Just filling in what I know, equals 2L, ooh, I don't seem to know that, dl dt, ooh, I don't seem to know that. So let's see which one we wanted. We wanted dl dt. So that should remain my variable, right? Which means that I need to figure out what L is. And so we can figure that out. If we know x is 3 and y is 4, then we're talking here about a triangle, a right triangle with sides 3 and 4. And so here L would necessarily have to be 5 at that point in time. So that helps me figure this out. So this gives me 3 minus 2 equals 10 dl dt. And so I can get that dl dt equals 1/10. And then let's grab our units. This would be feet per second. So what that means is at the instant when the rectangle has side lengths 3 feet and 4 feet, the diagonal is increasing at 1/10 foot per second. Okay, last one, and then we will work on these more after break. So let theta and radians be an acute angle in a right triangle. Let x and y respectively be the side lengths adjacent to and opposite to. And respectively here is going to mean in that order. Suppose that x and y vary with time. So we've got a dx dt and a dy dt. At an instant, x equals 2 and is increasing here. Y equals 2 and is decreasing there. How fast is theta changing? So on this, I did not give us an organizer because I want to be able to work through this. So let's start with a picture. So we have an acute angle in a right triangle. So right triangle, we'll make that theta, okay? And let x and y respectively be the adjacent and the opposite. So x has to be the adjacent, y has to be the opposite. So x and y. And that's all we know that's always true, right? There's other things that were given, but they're only true at a certain instant. So let's see what we know at is constant and then what's true at an instant. Okay, x and y vary with time. That's great. At a certain instant, x equals 2 and is increasing, which means dx dt will be positive at 1 unit per second. Y equals 2 and is decreasing at 1/4 unit per second. How fast is theta changing? So we're looking for d theta dt at that instant. So we need to come up with a formula that's going to relate x, y, and theta, right? Because that's what I need here. So you really got to dig into all the background stuff that you know. And for me, that is going to be that tangent of theta equals y over x. And so that's what I'm going to start with. So let's go for it. Let's take a derivative because there's nothing here that's always true that I could just plug in. So derivative of tangent theta is going to be secant squared theta times d theta dt. Y over x, to take a derivative of that, I'm going to use the quotient rule. So low d high minus high d low. Square the bottom and away we go, right? And so now this is a plugging in game. So I want to find d theta dt. I don't know secant squared, so this is going to be a problem. We're going to come back to it in a second. Now, x I know is 2. dy dt is negative 1/4. Y is 2. X is 1. And then x again was 2. And so I need to figure out what this secant squared theta is. And there's a couple different ways you could do this. You can figure out what theta is by looking at what x and y are, but there's all sorts of different things you could do. So here's how I'm going to think about it. I'm going to draw what I know, right? Which is that this is theta and x is 2 and y is 2, right? At this instant. And so what that allows me to get here is the hypotenuse, right? Because this would be 2 squared plus 2 squared equals the hypotenuse squared. So that would be 8. So this is square root of 8. And so now if I want to find secant of this angle, secant, remember, is going to be the reciprocal of cosine. So cosine of that angle is adjacent over hypotenuse. So 2 over 2 radical 2, right? Or 1 over radical 2. And so secant of that is just going to be the reciprocal. So secant here will be radical 2 over 1, and then I need to square that. Now, there's other ways to do that. You could look at this and say, oh, radical 2, that means this is a 45, 45, 90 triangle. But the easiest way, I think, to do it is to find the missing side and then figure out your secant from there. So this gives me just 2 d theta dt equals negative a half minus 2 over 4, right? So 2 d theta dt equals negative 5 halves times 1/4, which is negative 5 over 8. And so d theta dt is going to be negative 5 over 16. And let's look at our units, right? They told us that theta was in radians per seconds. And so notice the calculus isn't really much harder there. It's this whole plugging in and substituting in thing that gets a little tougher. So guys, we will work more on this. This last one was obviously trickier, and I hope you have a great rest of your break. I will see you next week.